All right, in the previous section, part one, we talked about how to find the given amounts when you have a principal and some time and a rate and a number of times compounded. So in the second part, we're going to actually figure out how can we figure out how long things take. So kind of a more interesting problem. If I invest some money into an account that has some certain parameters, how long will it take for my money to grow or shrink, I guess, depending on the account, in this scenario. So essentially, we're going to use our exponential equations with our logs and things like that. Obviously, we'll have to remember our compound interest formulas that we talked about in the first section of notes. A equals P, 1 plus R over N to the NT. And A equals PE to the RT. So this is normal compounding, and this is going to be when it is continuous. So we're going to plug some numbers in, and we're going to use a little bit of our knowledge of exponential equations to solve these. So the first one says, how long will it take for our initial investment of $1,000 to grow to $2,000 if it's invested at 6% compounded continuously? That's really important because that's going to tell me I have to use this equation. A equals PERT. Now, P is the principal. P is going to be the amount I start with, which is 1,000. The amount I want in my account is 2,000 after some amount of time. So we really don't know the time. And our rate is 6%, which is 0.06. So we know all these values, so we just have to solve and figure out what t is. So if I do this, I'm going to get 2,000 equals 1,000 e to the 0.06 t. So our base in this case, our base is this e, so I have to get that by itself first. So I'll go ahead and divide out by 1,000. That's going to yield 2 equals e to the 0.06 t. So when I'm changing to log form, remember log is an exponent, so this exponent will go by itself. So 0.06 t equals log. Now it's going to be log base e, which is natural log of 2. Remember, if you do natural log, just ln, that automatically assumes it's base e. Now if you did log base e of 2, that's not wrong, just not as clean. Then I can simply divide by 0.06, so my answer is going to be ln2 divided by 0.06. So that's how long it's going to take for my money to double from 1,000 to 2,000. So I'm just going to type that in the calculator, natural log of 2 divided by 0.06, and that's going to give me about 11.6 years. So it takes 11 and a half years for my money to double in this scenario. Now, a higher interest rate, it would take longer. A lower interest rate, or it would take shorter amount with a higher interest rate. A lower interest rate would obviously take more time. So here is another example. This one seems to be also continuously, because I see that. So where did that go? So it says continuously here. So we know continuously A equals PERT. So we'll try to figure out what these variables are. And if we've done it right, only one will be unknown, probably T. So when we graduate from college in 3 years, Angela plans to purchase a used car for $15,000. How much money does she need now so if she invests at an annual interest rate of 5% compounded continuously, she'll have enough to buy the car? So this one's a little different. So the interest rate is pretty simple, 0.05. But now what I know is I actually know T. It says in 3 years. We know how long we want this. But what we know is we want to buy the used car for $15,000 in 3 years. And we want to know how much do we have to invest right now. So what we really don't know in this problem is we don't know the principal. But we know the amount we want in 3 years is $15,000. It's a little different than before. So you will not need logarithms for this per se, because if I plug it in, I'll get 15,000 equals P e to the 0.05 times 3. Now this is just P times some number. Now it's a weird number. It's e to the 0.05 times 3. but I could simply just divide that out to both sides. So that will give me my principal. That will give me what I have to invest now. So obviously, if I've done this correctly, it should be a smaller amount than $15,000. And when I put it in the calculator, I get $12,910.62. So obviously, you just have to kind of figure out what variables are missing. A lot of times it's t. T is a very common variable to be missing, and you have to use logs and all that stuff. But you could really be missing any of them. You could actually be missing the interest rate as well. Okay, let's look at this last one. Now this one's going to be a little different because now we finally have one that is compounded monthly. So now we're going to have the other equation. We're going to have A equals P 1 plus R over N to the NT. And we're going to have to try to figure out what all of these variables represent in the problem. So it says we invest $5,000. So that's kind of a starting investment. So that's going to be $5,000. And an account earning 4% interest, so 0.04 for my rate, compounded monthly. Now that's going to be our N because if it's monthly, how many times a year do you get interest? Well, that would be 12 times. How long will it take for my $5,000 investment to grow to $1 million? So we want to know how long, and we want this to be $1 million. So I can tell you right away it's going to take a while because we're going from 5,000 to 1 million at 4% interest. So A is 1 million equals 5,000, which is my principal. 1 plus 0.04 divided by 12 to the 12t. I'm just plugging the variables in the formula. Now, if you notice, all of this is my base inside the exponential to the 12t. That's fine. I do the same idea. I would divide by 5,000. This is going to tell me how much bigger my money has to be. So 1 million divided by 5,000 is going to be 200. Equals 1 plus 0.04 over 12 to the 12t. So now it's base to a power equals a number. I can change it to log. So my exponent is 12t equals log. Now my base is this whole nightmarish number. If you want, you can just put what is 1 plus 0.04 divided by 12. And that base is 1.033. That's what this number turns out to be. And then it would just be 200. So I would probably figure out what that is on the left side first. Remember, the way we put it in the calculator is log 200 divided by log 1.033. So those are just buttons we can push in the calculator, right? Log 200 divided by log of 1.0033. So that gives me 12t equals 1,608.2, and that's just put in the calculator. And then I'll simply divide by 12 to get my time. So I get 134.0 years. So obviously it's going to take a long time for $5,000 to grow to $1 million if you're not making additional investments. You're just letting that money sit there. It's obviously going to take quite a while. Let's look at a couple other examples. So we have, if I invest $7,000 in an account earning 6% interest compounded continuously, how long to go from 70,000 to 7,000? So we got another continuous problem, so similar to the first one we did. A equals P ERT. So I'm starting with $7,000, and I'd like it to grow to $70,000. In an account earning 6% interest, and we want to know how long that takes. So no compounding, no n in this case because it's continuous. So 70,000 equals 7,000 e to the 0.06t. I'll divide out by 7,000. That's going to give me 10 equals e to the 0.06t. So again, now we have to use the log to get that variable out of the exponent. So logs are exponents, so 0.06t. And I'm going to use natural log of 10 because, again, it already has the base of e. Again, you can still use log base e. And then I'll just divide by 0.06. So whatever log of 10 divided by 0.06 is, I'm getting about 38 years, 38.4 years. Which seems logical because it's going to take quite a while for this money to basically grow by 10 times of what it currently is. Now, if you look at the next problem, so now instead of what if we're going the 7,000, same problem, but what if we're trying to go to $7 billion? So you would think that it's going to be a lot longer, obviously, right? But it's not always proportional. It's not like it takes a certain factor more, but it's certainly going to take me a while to get to $7 billion of growth. So 7 billion equals 7,000 e to the 0.06t. Very similar to the one we just did. So if I divide by 7,000, I get 1 million equals e to the 0.06t. So essentially we want our money to grow 1 million times over what it was, which obviously is a lot. So this is going to take a long time. So 0.06t equals natural log, so ln of 1 million. And so t is going to equal ln of 1 million over 0.06. Now, not surprisingly, this better take a while, so let me put this in my calculator. Now, ironically, it took 38 years to basically go from 7,000 to 70,000. Now, to go to 7 billion, it only takes 230.3 years. Obviously, a long time, more than will be around, but it's not like it's, 1 million times more than what it was. It's only, factor of like 6 times longer to go from 70,000 to 7 billion. So that's kind of this power of exponential growth. When it gets going, it really does get going fast. So hopefully nothing